Okay, here we go. 5-2. Let us preface this first with it will not go completely with your notes. So just make sure you follow with what you need to know. I want to say there's some extra stuff in there, but there's some missing stuff too. So just kind of bear in mind with that. I have not liked the way that this has gone the past couple of years, so I just revamped it. So probability rules in 5.2. 5.3 is going to carry on our probability rules, okay? Here we go. Here we go. The idea of probability rests on the fact that random behavior is predictable in the long run. We know that 50% of our coin tosses, provided it's a fair coin, good gosh, we'll make it. Uh-oh, somebody's in trouble. Yes, ma'am. I do. You bet. Mm-hmm. This is so much fun. Who thinks they messed up? Somebody park wrong? She didn't. It didn't sound like it was a bad deal. Was it? Okay. You sure? Okay. I really want to teach this less, but this is a whole lot more fun. Dang it. Hold on. That's all on record. Warmer. Warmer, colder. Miss Lynch. She said for just a quick second. I think it was you. It could have been you or you. Did you mess up? Because both y'all are close to. I know. I didn't think, she didn't sound like it was a mess up. Okay. Again, the idea of probability rests on the fact that random behavior is predictable in the long run. So in 5.1, we use simulation to imitate some random process. We wanted to see how feasible was it to get those 2 Coca-Colas or those 2 Pepsi bottles or those 23 boxes. We use simulation to see how likely that was or unlikely, okay? We don't always have to repeat this random process, whether it be tossing a coin, rolling a die, drawing slips of hat, many times to determine that probability of an outcome. We actually can find that mathematically, okay? This section, we're going to find it mathematically, the chances of things happening, as opposed to flipping a coin 50 times or 100 times to see how feasible things are to be, okay? So 5.1 is a really, really small section. It does help us understand a lot of things about statistics, but it's more really for the second semester stuff than it really is for probability, okay? So here we go. Chapter 2, we use normal density curves to find the chances of things happening. Don't forget that there'll probably be 1 or 2 questions off on normal distributions on this next test, okay? Chapter 3, we model linear relationship between 2 quantitative variables. Now we're ready to develop a model for random behavior. All right, so sample space, first one. It probably jumps around a little bit, but it's on there somewhere, okay? You need to know what the sample space is. It's a list of all possible outcomes. A list of all possible outcomes. If it's rolling a die, it's a 1, 2, 3, 4, 5, or 6. If it's flipping a coin, it's a head or a tail. If it's drawing a card, it's a 1 of 52 cards. Okay, it's the sample space. Sometimes it might be rolling a die and flipping a coin. So it'll be the 1 in a head and a 1 in a tail, and a 2 in a head and 2 in a tail, 3 in a head, 3 in a tail. Okay, it's just every possible outcome. That is the sample space. List of all possible outcomes in whatever chance experiment we're dealing with, okay? Roll a die, the chance experiment, 1, 2, 3, 4, 5, or 6, okay? So you'll have some questions tonight, say what is the sample space? And luckily you don't have to list them all because it's multiple choice. You just get to choose which one is listed them all, Okay, pretty easy idea. Event is the probability of a single event. Okay, what does it say? Any collection of outcomes from the sample space. So the event might be rolling a 1, rolling a 2, getting ahead and a 2. So the event is any outcome from that sample space. They'll tell you what the event will be. They'll tell you what the event will be. So it's any outcome from that sample space. I told you guys, I'm sorry, I apologize for those notes bouncing around. I had a choice of giving you new notes or just kind of fill these in as we go, and I think that probably will be better than you just trying to keep up with loose papers. We'll see how this year goes. This is trial run. I went back to my original years for this. Rolling a prime number, 2, 3, 5. 1 is not prime. Okay, events are usually designed by capital letters like A, B, or C, or so on. 4, rolling 2 6-sided dice, we can determine event A as getting the sum of 5. Okay, so a lot of times that's what they're going to do. They're going to designate some variable, and usually it's a capital letter. Just recognize all this stuff as some event. And so they're going to say the sum is 5, and they're going to call that event A. That way they can say the probability of A rather than the probability of the sum of 5. Okay, so typically we write it as this big P, A. Or we could write it as the probability of the sum is 5. Either way is acceptable. I just want you guys to recognize the notation. Okay, anytime you guys see it, and we did a little bit with normal distributions, but anytime we see that, that's the probability of. I may have sent the wrong person. I think I did. Yes, ma'am? I told you. Okay. He's on his way. Bye. I knew I wasn't listening. Chris Critica. Close. Close. All right, shut up. All right, so big P. Big P is always the probability of something, okay? Probability of something. So a probability model, what this is a probability model. It consists of 2 parts, and the 2 parts it has the sample space, and you know what the sample space is. You know what the sample space is. The sample space is all possible outcomes or all possibilities, okay? So it has the sample space, and then it also has the probability of each outcome. We'll do a couple of these just to make sure you understand what it says. Typically, this is done in table format. Typically, it's done in table format. For instance, if I wanted to roll a dice, the sample space is a 1 and a 2 and a 3 and a 4 and a 5 and a 6. So that's the X value, okay? And then they'll say the probability of X, and each of these are 1/6. So that is a probability model. It gives me every possible outcome and gives me the probabilities of each one, okay? Sometimes they're the same probability all the way across, and sometimes they're not. We're going to be dealing with some that are and some that are not. So that's a probability model. They're going to ask you some questions tonight. Is this a legitimate probability model? So I'm going to make sure that comes up next. Okay, that's what a probability model is. To be a valid probability model, it must, 2 things must happen. All the probabilities better be less than 1 or greater than 0. They have to be less than 1 or greater than 0, which that makes sense because we've never seen a probability greater than 1 or less than 0. So they all have to be that way. But then the other deal is they all have to add up to 1. Because guys, if they don't add up to 1, then we don't have a sample space because you don't have every possibility. You're with me on that, right? It has to add up to 1 because that's the sample space. It's all of them. So if it's all of them, it has to add up to 100% of the data. So to be a valid probability model, it must have those 2 things. Every probability must be between 0 and 1, and they all have to add up to 1, okay? They're going to ask you some questions on your homework. There's going to be one on your test. Is this a valid probability model? Yes or no, and why? Well, because all the probabilities add up to 1. There's another one at one time, again, where whoops, sorry. I can't do that with this one. I have to do this. Remove one of those, and I say, what is the probability of 4? This one's really easy because you can see that you got 5 6, so you have 1 6 left over. Okay? All right. It's my fault. I was the wrong one. That's okay. Good exercise for you. You're welcome. Dang it. I knew as soon as I said it. It's okay. It's good practice for you. I should have sent 3 others. And then nobody would have known who it was. Okay. Here we're going to start. Rolling 2 dice is a common way to lose money in a casino. Notice that, right? Imagine rolling 2 fair 6-sided die. I'm rolling 2 fair 6-sided die. One is to help alleviate some issues. We have a red one and a blue one. Okay? How many possible outcomes are there? Nope. 36. There's 6 possibilities for the first one. There's 6 possibilities for the first one. And there's 6 possibilities for the second one. So anytime you're trying to figure out total possibilities, that's what you do. If I'm rolling a die and flipping a coin, rolling a die, flipping a coin, there's 12 possible outcomes. Okay? You just take, it's called the counting principle. You don't have to know that, but it really is helpful for this class. Okay? So you take how many possible on the first one, how many possible on the second one, and multiply those together. Guys, shh. Okay? So, are every one of them equally likely? Every possibility is equally likely. The sum is not equally likely. The sum is not equally likely because it's harder to get a 1 and a 1 than it is a 7 and a 4 and a 3, or a 7, I should say. I'm sorry. Okay? It's harder to get the sum of 2 because there's only one way to get the sum of 2, whereas the sum of 7, there's a lot of ways. But every possible outcome is equally likely. It's all 1 in 36. Those are all 1 in 36 possibilities, right? 1 and 1, so all these are the 1s with the 1, 2, 3, 4, 5, 6. Then all the 2s with the 1, 2, 3, 4, 5, 6. Where you end up with a 6 and a 6, you start with a 1 and a 1. Good enough for that? That's all possibilities. So that is what? The sample space. This is the sample space because that's all possible outcomes. Okay? Let's say let A get the probability or getting a sum of 5 when 2 fair die are rolled. All right, so 5, 5, 7, 6, 5, 5, 5, 5. 1, 2, 3, 4 possibilities. Okay with that? That is the event. That is the event. And that probability is 4 out of the entire 36. Remember what I told you guys in class. You can leave it as a fraction. You can reduce it. You can turn it to a percent. You can leave it as a decimal. They don't care. They don't care. So I would just leave that as 4 out of 36, and I wouldn't do anything else because that's taking up precious time that I don't have. Good enough with the event. A sample space can be very simple, or it could be very complex. If we toss a coin once, there are only 2 possible outcomes. That sample space is really easy, heads or tails. When a Gallup takes a random sample of 1,523 U.S. adults and asks a survey question, the sample space consists of all possible sets of responses from that 1,523 with over 240 million possibilities. That's a really big sample space. The probability model does more than just assign probability to each outcome. It allows us to find the probability of an event. So here we go. I got a spinner. Red, blue, yellow. Looks like it's equally distributed. A spinner has 3 equal sections, blue, red, and yellow. Suppose you spin the spinner twice. Give a probability model for this random process. Well, probability model needs what? 2 things. It needs every outcome and needs a probability of each one of them. So let's go every outcome. I don't know. Red first. Red first. Well, if I get a red first, I could get a red second. If I get a red first, I could get a blue second. If I get red first, I could get a yellow second. That's 3 possibilities. Now I could get a blue first. And I could get a red, I could get a blue, or a blue and a yellow. And then the last one I could get now is a yellow first. Yellow, red, yellow, blue, and yellow, yellow. Good enough with that sample space. It wants the probability model. Well, I need the sample space plus the probabilities associated with each one of them. Well, how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. I should have known that to begin with because what? There are 3 possibilities the first time, and there are 3 possibilities the second time. So there's 9 possibilities. You should that should help you validate that you know you got 9 different ones. Okay? And each one of them are what? Is equally likely as the previous one. So if they're all equally likely, then they're all 1/9 of a chance. They're all 1/9 of a chance. Any questions about that probability model? Any questions? Red, 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 blue, blue, yada, yada, yada. And then we're each one of those with 1/9. You could do it like the way I did it. Just understand you got multiple choice on this stuff, so it's going to somewhat do some, it's going to make some tables like this for you. Okay? Okay, that's the sample space. I'm sorry. This is the sample space here, right? This is the probability of each one of them, and therefore that is a probability model, okay? Define event A as spinning a blue at least once. Blue, 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 blue. Find the probability of A. 1, 2, 3, 4, 5. As simple as that looks. Don't worry, we're going to get hard. But that makes, we got to get the easy ones right. Okay, blue at least once. If we want a blue twice, we'd only have 1 out of the 9. If we want blue on the first, we only have 1, 2, 3 out of those out of 9. So they can ask several questions from that, and that's what they're going to do with your homework. They're going to give you some probability model, and they're going to ask you 2 or 3 questions from that probability model. Complement rule. This is going to bounce around quite a bit on your notes somewhere. Complement rule. Okay, here's the complement rule. You guys are beautiful. Complement. Here. I hate you guys. The complement rule. So here's what they're going to do with this. They're going to tell you some variable, and they're going to raise it to the C power. That's the complement. That means it's not A. It's not A. Who's dinging? By gosh, fix that. It's not A. It's everything but A. It's everything but A. So if A was an even number, then the complement would be an odd number. The complement is everything but that one, okay? It's a really important one that you need to know, and it's one that you don't think about a whole lot until you really, really need it. The complement rule. We're rolling 2 fair dice. What's the probability that the sum is 6? Fix it. Fix it. And I've been on these notes a lot of times. None of them ding. Probability is 6. Let's see. 1, 5. 2, 4. 3, 3. 4, 2. 5, 1. 1, 2, 3, 4, 5. Okay with that? Did I count? Did I get them all? 1, 5, 2, 4, 3, 3, 4. Okay with that? Guys, sometimes it's just easy to try to figure it out mentally just to count them. Sometimes it's just quicker to count them. You know there's 36 possibilities because there's 6 possibilities on first and 6 possibilities on the second. That gives me 36. Then you just got to figure out how many times it's a 6. Okay? If we roll 2 fair die, what's the probability that the sum is not 6? Well, we already know that the probability is a 6 is equal to 5 out of 36. So the probability that it's not a, whoops, sorry, dang, the probability that it's not a 6, and that's what they're going to do. They're just going to raise it to that C power, okay? They might use prime, but most of the time it's just a C. is whatever's left. Okay? You don't even have to figure anything out because you know it's the complement of it. It's the what's left over. There were 5 here, so there has to be 31 here. Complement. Complement. Next word. Mutually exclusive. Mutually exclusive. Or disjoint. It may be called either one. It may be called either one. Mutually exclusive. It might be called disjoint. You're going to have two events where neither one are in common with each other. They have no outcomes in common. They have no outcomes in common. They're mutually exclusive. No outcomes in common. Mutually exclusive. It's impossible to roll a die and flip a coin and get the same thing. Those are mutually exclusive events. It's impossible to get the same thing. They have nothing in common. Mutually exclusive or disjoint. Most time they use mutually exclusive, but you might see disjoint every once in a while. Both of those words mean the same thing. It's one of those definitions you got to know. One of those definitions you got to know. So what that means is this right here, guys. We're starting to get into some of this probability and calculating these probabilities. That means we have the probability of A and the probability of B. This might be the probability of a 1, and the probability of B might be a tail. Whatever those two probabilities are, that probability is a 0. There is a 0 chance of that happening because they cannot happen at the same time. And means they both have to happen. You have to be a senior and you have to be in AP Stats. Those are not mutually exclusive events because they can happen at the same time. We can have a senior that's in AP Stats. I don't think you can have a first grader that's in AP Stats. Therefore, those are mutually exclusive events. Because the probability of that happening is 0. It can't happen. Okay? You've got to be able to associate that statement with mutually exclusive. You've got to be able to do that. I debate about telling you or showing you this one or not, but I will. I'll show it to you. If they're mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B. If they are mutually exclusive, only if they are mutually exclusive does this work. That's why I debated about telling you this. If you want A or B, the probability of a senior or the probability of an AP Stats, then it's the same as the probability of being a senior. Well, those are not mutually exclusive, so it doesn't work. That's a bad idea. First grader or AP Stats. Those are mutually exclusive. The probability of being a first grader or the probability of being in AP Stats. Add those two together, and that's the probability of OR. Okay. Were you able to follow the notes somewhat? Okay, that's that. That only works for mutually exclusive disjoint events. That formula does not work for anything else. You won't see that formula on the formula sheet. There's another formula you'll see on the formula sheet. All right, here we go. Here we go. Let's see if we can put some of that stuff I've told you guys into this problem. I tear open a corner bag of M&Ms, milk chocolate candies, the delicious candies that melt in your mouth and not in your hand. Oh, it doesn't say that. Pour one candy out under your hand. Observe the color. According to Mars, the maker of M&Ms, the probability model, the probability model means it's all possibilities. From its Cleveland factory is blue is 0.207, so it's almost 21%. Orange is just under it. Green is under that. Yellow, then red, and then brown. I don't think that makes sense. It seems like all mine are brown. But neither here nor there. Everybody okay with all that? Beautiful? Let's see what their question is. Uh-oh, good catch. Explain why this is a valid probability model. Well, my guess is that that number plus that number, plus that number, plus that number, plus that number, and that number is 1. And so you have to show it. All probabilities are less than 1. And how about this? Sorry. How about this? Beautiful. They're less than 1, greater than 0, and all the probabilities add up to 1. You would do that differently if that was a question on a test. You would show that step, right? Show how they're all added up, and it equals 1. The probability of each outcome is a number between 0 and 1, and the sum of the probabilities is boom, 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 1. Questions? That's easy. That's easy. I hope. Find the probability I don't get a blue. Two ways to do it. Add up orange, green, yellow, red, brown, or take blue and subtract it from 1. Either way, they don't care. It's probably easier to subtract 0.207. Making sure you don't what? Have a naked answer. Never have a naked answer. Never. Never, 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 never. 0.793. Easy enough? Not a blue. 793. Good math. Not a blue. And if you didn't want to do the 1 minus and you wanted to do the other 4 plus, that's fine. Yep. Just as long as you got this part. Something. I couldn't do B because we have a brown. I could have done BL, I guess. Is that fair? Anybody? She said, do I want you to write, like, we got to write probability of something. I don't care if you said not blue or blue complement or however you want to say that, that's fine. They didn't care. Sometimes they'll tell you how to write it. What is the probability you get a brown or an orange? Okay, well now I got to understand, are these mutually exclusive events? In other words, when I pour one of those M&Ms out, can I get a brown one and a green one at the exact same time? Not off of one. I get 2 out, I could get a brown one and a green one, but that's only if I got 2. They cannot happen at the same time. It's impossible to pull one of those out and be at brown and green. And if it is, I'm taking them back because I'm nervous. Good enough? So because they're mutually exclusive events, I can take the probability, here we go, I want orange or brown. Okay, they didn't give me any letters to use, so I can't use any letters. I'm just going to use brown or orange. And I didn't spell orange all the way, and that's okay. They don't care. And then I'm going to go to orange, and I'm going to go to brown, and orange is 0.205, and brown is 0.124, and we're going to get 0.329. Man, I told you guys this was hard. I lied, didn't I? Good. I don't want it to be hard. I want it to be easy. Who has a question about that? I threw this in. Suppose we choose an American adult at random. Define 2 events. This is what's common. This is what you'll see a lot on your book. This is what you'll see in AP. A, the person has cholesterol level of 240 milligrams per deciliter of blood or above. B, the person has a cholesterol level of 200 to 240. According to the American Heart Association, this is 0.16 and that's 0.29. Y'all okay? Do I have the sample space? Do I have a sample space from this data? 0.29, 0.16. I'm missing some people. How do I know? That doesn't add up to 1, right? There are other people out there that may have it below 200 or may be way above 240. I don't know. But however it is, I don't have all of them. Okay? Explain why events A and B are mutually exclusive. Well, they're mutually exclusive because it's impossible to be above 240 and be below 240. Can't. You're either one or the other. Let C be the event that let's, in plain language, what's the event A or B, and then find the probability of A or B. So that's the probability of having someone that's 240 or above, or someone that's 240 below, but above 200. And that's just simply a, 30, 46, 45%. So almost half. Let C be the person chosen has a cholesterol level below, find the probability of C. Oh, so maybe that's everybody that's left. I guess that may be everybody that's left. I guess it has to be, right? You're either above, or you're between, or you're below. So that's everybody that's left. All right. This is where you're not going to find your notes. AP, I told you guys this is like the 4th book I've used. And all 4 books have used a different way to solve these kinds of problems. They use two-way tables. They use Venn diagrams. They use tree diagrams. And in all my years, the two-way table is the best. And so that's all I'm teaching. I'm not teaching the other ways. I'm going table, 100%. And if you don't like the table, come see me, and I'll give you the other way. Fair enough of what I'm saying? But I think, after all these years of doing this, I think going one way is better than trying to go 3 ways. So, when you're trying to find probabilities involving 2 events, a two-way table can display the sample space in a way that makes probability calculations easier. So, bear with me. That's already a two-way table, so this one's going to be really easy. We've already seen some two-way tables. We saw them in chapters 1 and chapters 2. Students in the college statistics class want to find out how common it is for young adults to have their ears pierced. They recorded data on 2 variables, gender and whether or not they had piercings or not. For all 178 people, and you can see there are 178 people that were asked or looked at or whatever they did. There's the 178. The two-way table summarizes the data. So let's soak that up for just a second. We have gender, male, female. We have ear pierced, yes or no. Pretty simple little study. So there's the 178. We can see that there were more males than females, but not by much. There were only 2 more males than females. And there were a whole lot more ear piercings than non-ear piercings. Okay, beautiful. Suppose we choose a student from class at random. So I'm choosing some student at random. It's out of the 178 students. Define event A as getting a male student and B is getting a student with a pierced ear. So we have a probability of A is male and the probability of B pierced. I don't have to write that. That's just what they're telling me. It's way down at the bottom. Some of you guys may not can see it. Find the probability of B. And B was what? Male? Oh, B is pierced ear. Oh, B is pierced ear. So pierced ear. Well, how many are pierced ears? 103 out of the 178. Leave it like that, reduce it, change it to a decimal, change it to a fraction, write it as a percent. They don't care. I'd leave it like that. It does come to 0.579. Okay? Beautiful. Any question about that? Easy? Find the probability of A and B. All right, now we got to go back to what we think. First of all, let me ask you this. Are these mutually exclusive events? Like, can you be a male and have a pierced ear? So those are not mutually exclusive events. Okay? They're not. Those are the two events. Okay. I want the probability of A and B. That means they have to be male and they have to have a pierced ear. They got to be both. They got to be both. These are all the males. These are 90 males, but 71 of those cats don't have a pierced ear. 19 of them have a pierced ear. So that's 19 of those guys that I'm looking for. But it's 19 still out of what? All of them. Because I'm just drawing one person. So it's 19 out of 178. Again, I hope that this is fairly easy for you. It becomes a little bit more difficult when you don't have the table. You have to make the table. And that's going to come up in a little bit. Okay? Y'all okay with a 19 out of 178? It has to be the common. It has to be the common because it's and. That's 0.107 if you need it. The last one is find the probability of A or B. Now, if you hadn't paid attention, pay attention to this because this is the most missed question. This is the most missed question. Because here's what students will do. They're going to say A, which is what? The probability that they are a male. And they're going to take these males, which is 90 of these cats. And then B is the probability of a pierced ear, and they're going to take these 103 cats, and they're going to add those two together, and they're going to put 193 out of the 178. And hopefully that says to you, wait a second, that's wrong. There's no way it's over 100%. Okay? The one on your test doesn't do that. So you won't get a little heads up of, I've messed up. But here's what you've done. You've added that 19 twice. You've added that 19 twice because this 19 goes down here, but it also goes across there. So I don't care how you do it. One of three ways. Take the 71 and the 19 and the 84 and add them. Take the 71, the 19, and the 84 and add them. Take the 90 and the 103 and subtract the 19 because you added it twice. Or my preferred method, take the 178 and subtract those four because those are the only ones that are not male pierced ear. And that's the easiest way to do it. Because anytime they want the or, they basically want everything but that one. And so the easiest thing to do is take the 178 and subtract that 4. But I don't care how you do it. And there may be some problems that you may not be able to do it that way, and you may have to do it a different way. The ors are the ones that get students. The ands don't get the students. The single ones don't get the students. It's the ors that get the students. And again, it's because we just get in the habit of doing these guys right here. Just think about it. You've added that 19 twice. Okay? Beautiful. Beautiful. That comes up to 0.978 because it is 174 out of 178, which is almost all of them. Part C, this is emphasizing what I've just told you, okay? Part C reveals an important fact about finding the probability of or. We can't use the addition rule. Remember that addition rule I just told you, or was a probability of A plus the probability of B. That's what the rule was I just gave you. But that's only for what? Mutually exclusive events. And these were not mutually exclusive. So you can't use that formula, which I emphasized already. But that's where some students mess up, right? The outcomes here are double counted with that 19. So this is just emphasizing everything I talked about. And so you have the 90 and the 130, and then you have to subtract the 19. This is the formula that's on your formula sheet. Right there. That's what's on your formula sheet because that works every time. And that's what I was going to give you to begin with because that works always. They say the probability of A or B is equal to the probability of A plus the probability of B, but then we're going to subtract the probability of A and B. Because that's the common thing that you've added twice. And that works whether they're mutually exclusive or not. Why? Because if they're mutually exclusive, what's the probability of A and B? 0. If they're mutually exclusive, that's 0. And so that formula is what's on your formula sheet because it works every time whether you're mutually exclusive or not. If you are mutually exclusive, that's 0. You may or may not need that formula. I don't know. I don't think I use it very often at all, if I ever do. Okay, how are we doing? Kind of bounced around a little bit. Can y'all still follow? We're good? We're not completely done, but we're getting close. We're getting close. Okay, notation. So again, I mentioned you guys a lot of times, us mathematicians, we're lazy. We're lazy. Rather than write A and B, they'll write intersection. That looks like an N. That looks like an N. So that's A and B. A and B. The or is called a union. And so it looks like a U. But that's or. 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 And can't mess that one up. And or you can kind of mess up sometimes, but or can't even say it right. Okay, just a notation. Just a notation. We get lazy. I know, 3 letters, 1 notation. But you do it enough times, now you're saving some writing. Okay? So this one's called the intersection. It's where they intersect. Okay? That's why they call it the intersection. It's where they intersect. It's where they intersect on the table. And then the union is or. It's all of them, but that one. All right, here we go. This is going to test if you can understand anything at all. I'll try to go as slow as I can because if you don't get this, this chapter is brutal for you. A survey of residents in a large apartment reveals that 68% use Facebook. 28% use Instagram. 25 do both. Are these mutually exclusive events? Can they happen at the same time? Can you use Facegram and Instagram? I'm sorry, Facegram. Instagram and Facebook. Yeah, I guarantee it, 25% use both. So they're not mutually exclusive. You can't just use Instagram. Okay? So we're going to select at random. What's the probability the person uses Facebook or Instagram? Here's the way I'm going to work this problem. Every time I'm going to make a table. And so one of these sides, I don't care if you want to do it on the top or you do it on the side, but one of the variables has to be on the top and one of the variables has to be on the side. Listen to me again. One of the variables has to be on top. One of the variables has to be on the side. I don't care if you want to put Facebook on top or Facebook on the side. If you put Facebook on the side, you got to put Instagram on top. So whichever one you want to do, you're going to make a table. And I put a box and then I put my little tic-tac-toe in between it. Okay? A box with a tic-tac-toe. And whichever one you want to put, this is Facebook, not Facebook. Listen to me, don't mess this up. Facebook, not Facebook. Don't put Facebook, Instagram. Whatever variable you put on top, it's the not. It's the yes and the no. And then the last one is just a total. The last one's a total. And then we're going to put Instagram or not. Total. And I don't care how you do that. You don't have to put yes and no first. You can put no and yes. But you just got to have a yes and a no, or a no and a yes and a yes and a no. You can't have Facebook, Instagram. That can't work. Okay, and now we're going to fill this thing out. And here's what it says. It says 68% use Facebook. 68 use Facebook. That goes down here because that's 68. That's the total. So use your easy math here. If this is 68, this has to be 32. Why? Because you either use Facebook or you don't use Facebook. And so if 68 use it, that has to mean that 32 don't. Then what else do they tell me? They tell me that 28 use Instagram. So 28 is going to go here. That must mean that 72 goes here. That's a 1. That's 100% of the data. And boy, I sure hope they gave me something else to fill this thing out. And luckily they did. They say 25% use both. And so this bad boy right here becomes 25% because those are the cats that use both. This is like the easiest one to fill out. And so this 25% from this 68% gives me 43%. So there's 43% right there. And now this 25 with this cat over here is 0.03. And that 43 and that 72 is 0.29. Yeah. Sometimes I need to do a calculator to do some subtraction. And now, guys, they can ask me any question they want on this thing. I don't have to use a formula. I don't have to use tree diagram. I'm going to use this table just like we use in that example. And what is their question? What is the probability they use Facebook or Instagram? And you can do that 3 different ways. You can do 68 and 28 and subtract 25. Or you can do 43, 25, and 3. Or you can do 1 minus 29. Either way. And what's nice is this validates as your work. So there's nearly nothing else to show. You want the probability of Facebook or Instagram. So they'll count that. Make sure you write that. And now we're just going to do, I'm just going to do 1 minus 0.29. What am I left with? 7.1. Question. Here's where students mess up on their tables. They don't put the same variable on top. They use a variable and another variable. Don't do that. Whatever variable you choose, whichever one, it's a yes and a no. There are sometimes you'll have a high school, college, master's. Okay? So sometimes it won't be just a yes, no. It may have 3 options. So just be aware of that. Most time there's only 2. Beautiful. Here's the next question. I don't think they're done. Oh, many probability problems involve simple computation that you can do on your calculator. It may be tempting to just write down your final answer without show supporting work. Please don't do that. A naked answer receives always no credit. Even if it's correct, you'll get penalized. So show something. You did something to do it, okay? All right, beautiful, beautiful, beautiful. TV, drama, comedy viewers, and health information describes a large survey that was conducted by the Centers for Disease Control, CDC. Let's investigate these events. L, the event that a randomly selected adult male reports learning something new about health issues or disease from a TV show. So you learn something from it. F, the event that the randomly selected is a female. So we got F, female, learn something. Good enough? Data from the survey were used to estimate the following probabilities. There's L, 0.58. That must mean that 0.42 didn't learn anything. And F was 0.5. That must mean that M is 0.5 or not F. And L and F is 0.31. That's that intersection. Okay, those are the easy ones to do when they give you that intersection. Okay. What is the probability that a randomly selected adult has learned something about new or a disease TV show from the previous 6 months? Oh, I'm sorry, or is female. And so that is almost the exact same question. Okay. I wished I would have changed that and giving you the or right here. So you don't have this on your paper anyway, so just predict it, just follow along with this. I don't know if this works. I don't know if this works. This is the one that makes it a little bit harder for students. Here's my table, tic-tac-toe. Female, male, learned something, didn't learn something. Total. Female, male was 0.5, 0.5. Learned something was 0.58. 0.5. Now, again, play along. I got the or, which is 0.31. I got the or, which is 0.31. That means, oh, that's impossible. Yep, that's bad. Sorry. That means that this plus this plus this is 0.31. Maybe it still works. This plus this plus this is 0.31. But it means that this has to be 0.69 because that's what's left over. And so because this is 0.69, which doesn't work, I didn't think it would. Now you can figure out what this is, then you can figure out what this is, then you can figure out what this is. Fair enough with all that? I'll fix that for next hour. Sometimes people call the emergency center number to report situations that are not considered emergencies, such as a lost dog. M, the next call to 911 is a medical emergency. N, the next call to 911 is not a medical emergency. It's just some emergency that somebody thinks. Suppose I know that the probability of M is 0.3 and N is 0.20. Uh-oh, they should give me some more information. Here's my table. M, not M. N, not N. Total. M is 0.3, 0.7. N is 0.2, 0.8. They didn't give me anything else. Crap. I need somebody to use their brain. Gosh, dang it. It'll hit somebody in a second. Bonus points. Now we start thinking. Why is it 1, not 2? They're mutually exclusive events. They can't be a medical and a non-medical emergency. That's 0. Fair enough. You got to kind of recognize those type of things. Okay? And that's why we do it in class, because I used to not do that in class and expect you guys just to figure it out. Stupid me. Those are mutually exclusive events. They can't happen at the same time. They can't be a medical emergency and a non-medical emergency. It's one or the other. So because of that, there's no intersection because it's a 0. The probability of this happening right here is 0. Well, if this is 0, then this has to be 0.3. And if this is 0.3, this has to be 0.5. And if that's 0.5, that has to be 0.2. And now we can ask any questions out of that table. What's the probability that it's either one or the other? Well, it's just 0.5. But I knew that without having to do the table because I knew they were mutually exclusive. I didn't have to add the and. But you had to think that they're not mutually exclusive. And you can get it from the table just as you can is easy from the formula, at least in my case. Some of you guys may not. I don't know. Because events M and N are mutually exclusive, the next call will be both a medical emergency and a call that's a non-medical. It can't happen. Okay. They do sometimes do these with a Venn diagram. If you're comfortable with Venn diagrams, go ahead and use those. I don't use them. And I'm not going to teach you to them, but it's the same type deal. You would have a circle and a circle. And one of those would be FaceGram and one of those would be Facebook and the other would be Instagram, and this would be both. That'll be the both. And then what's ever out here is the none, the neither. So it works if you'd rather do a Venn diagram. I just don't do them. There's the Venn diagram of the pier steers. Okay, I think you have enough information to get through today's lesson. Give a probability model for the chance procedure with equally likely outcomes and use it to find the probability of an event. Use basic probability rules, including the complement rule and the addition rule for mutually exclusive events, and use a two-way table or a Venn diagram. We don't use a Venn diagram. I turn everything to two-way tables to find chance process and calculate the probabilities. I hope. Bad part is I don't see you guys again till Monday, right? So let's get that assignment done by Monday. And then you guys, please ask questions. I'll give it to you on Monday. I'm sorry, but for your benefit, I'm giving you a worksheet that you're going to hate, but I guess I don't care if you do it or not. If you don't, it'll show. I love you guys. It should be posted, I think. Let's use our time today wisely and work on our assignment. Por favor.